Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is module 23 in my computer networks lecture series, where we talk in a little bit more detail about TCP sequence numbers and the ARQ algorithm that is implemented at the TCP level. And so to start off, I'd like to talk a little bit about how sequence numbers work, because up until now, we've talked about sequence numbers before back during the data link layer discussion, but the sequence numbers were basically frame numbers. So the first frame had sequence 0, second frame had sequence 1. At the TCP level, if you'll recall from the previous module, the TCP layer provides kind of a byte stream abstraction to an application. So an application doesn't have to worry about, dividing things into packets. It can just write basically a whole stream of bytes, maybe a big array or a data structure, to the TCP layer. And then the TCP layer is responsible for dividing it into packets. And so the TCP layer will basically take the bytes that it receives from the application layer and chop it up into pieces called segments. And segments you can think of as essentially a TCP packet, at least for the purposes of our examples. A segment is a packet. And each segment is assigned a 32-bit sequence number. So the sequence number is quite large. And the sequence numbers are basically for the bytes contained in the transmission and not the segments. So, for example, if one packet that contains 5 bytes of user data has a sequence number of 100, then the next packet will have a sequence number of 105. So the sequence number is essentially the byte index of the very first byte contained in the segment or packet. And we'll do an example, and this will be reinforced. The initial sequence number used by TCP can be randomly chosen. It can basically be anything. Practically speaking, you'll see 0 a lot. A lot of protocol stack implementations default to 0. That's going to be the case when we look at a TCP exchange in Wireshark, but just be aware that it doesn't have to be 0 all the time. And separate sequence numbers are maintained for each traffic direction. So most TCP connections are bidirectional. Data is sent from, in both directions between the nodes, and each direction has its own sequence number. So, as we mentioned in the previous module, TCP uses ARQ to deal with lost and out-of-order packets. The error detection scheme it uses is the 16-bit internet checksum that we studied back when we looked at error detection. Practically speaking, it's not super common for a packet to arrive at the TCP level and have a few bad bits in it. Typically, the packet arrives intact or it doesn't arrive at all, because again, when packets are lost due to router buffer overflow, it's not as though those packets are somehow corrupted but still make it through. They're just simply dropped. They just simply disappear. The ARQ algorithm used by TCP is the selective repeat ARQ algorithm, which is the most general implementation of the sliding window protocol. So if you'll recall, we introduced the idea of selective repeat ARQ back in module 9 when we introduced the sliding window protocol. And it's essentially the same. We're going to do an example in the next slide just to demonstrate this, but it's essentially selective repeat ARQ. The transmitter and receiver maintain a window size of, W, but the window size is specified not in terms of number of frames, but number of bytes. And that's an important distinction. But other than that, it's pretty much exactly the same. Several segments, and recall a segment is essentially a packet. Several segments up to a total of W bytes can be sent without an acknowledgement, so that's the transmit window. Acknowledgements, however, may come sooner, and they are typically piggybacked on return data packets. And you'll see this especially when we look at an actual TCP exchange. ACKs sometimes are sent just uniquely, but they're also very, very commonly piggybacked on data packets that are coming in the opposite direction. The receiver, of course, will buffer out of order sequence segments, and the acknowledgement contains the sequence number of the oldest byte the receiver hasn't received yet, or the index of the byte that the receiver is expecting next. So now we're going to work through an example where we have two nodes communicating with each other. And I'm going to use essentially exactly the same notation that I did back in Module 9 when we introduced the sliding window protocol. So if you need a refresher on what NTX, NRX, NS is all about, please review your notes from Module 9. I'm going to dive into the example, and we're basically going to see that this is exactly the same as the general sliding window protocol we did, or similar to this general sliding window protocol that we did in Module 9, except the main difference is how the sequence numbers work for TCP. So again, the sequence numbers are going to be byte indices rather than frame numbers. So let's start out by sending a packet from node 1 to node 2. And for the purposes of this example, the sequence number is going to be 100. So our initial sequence number is going to be 100. This is our initial sequence number. Often you'll see the initial sequence number being 0, but it doesn't have to be that value. And the size, or the payload, of this segment is going to be 8 bytes. So we're carrying 8 bytes of user data in this TCP packet. NTX, if we take a look at our system values at this first point, represented by the gray line, NTX is going to be 108. So NTX is the sequence number of the frame or segment or packet that we want to send next. And remember, the sequence numbers are byte indices. So if we started out with sequence number 100, we have basically sent bytes 100, 101, 102, 103, 104, 105, 106, 107. Those are the indices of our 8 bytes. And then it's byte number 108 that we are going to transmit next. So NTX is equal to 108. Byte number 108 is also what is being expected by our receiver. We haven't lost or received any out of order packets yet, so NS and NRX are the same. We're now going to send an acknowledgement back to from node 2 back to node 1. And that acknowledgement is going to be the byte that our receiving node 2, is expecting next. And so the acknowledgement number is going to be 108. And so at this next time point, NTX is still 108 because we haven't sent our packet yet. Our acknowledgement, most recent acknowledgement that we've received, however, now is 108. and NRX and NS haven't changed. And so now let's look at a situation where we send another segment. And rather than waiting for an acknowledgement, because we don't have to, we send a second packet. However, this second packet is lost. And remember, over here, don't forget about our window size, right? So our window size is 12 bytes. And so that means we can send up to 12 bytes before having to stop and wait for an acknowledgement. And so let's say this first segment that we send, whoops, I don't know why I'm so bad at drawing cues, has sequence number 108, and its size is 6 bytes. So we're allowed to send up to 12 bytes before having to wait for an acknowledgement. So rather than waiting for an acknowledgement, we send a second frame, which will have sequence number of 114, right? Because that's the index of the first byte in this second segment. And let's say for the purposes of this example, we only send 2 bytes in this second segment. So let's catch up a little bit with our acknowledgement variables. So at this point, we've sent sequence number 108 with a size of 6. So the next frame or the next segment that the transmitter is going to send, node 1 is going to send, will have a sequence number of 114. That's the sequence number expected by the receiver as well. And then once we have lost, and then our acknowledgement is still 108. And then at this point, our acknowledgement is still 108. The sequence number the transmitter wants to send next is now 116. However, the packet that we've received is the most recent packet that we've received, the next byte that we expect at the receiver is still 114, and NS is still 114. Now, even though we've already sent 2 segments, we still haven't filled up our window size of 12. And so what I'm gonna do is allow the transmitter to send 1 more segment. And we're running out of space a little bit here, so I will try to kind of move things a little closer. And so for this last segment that we send, sequence number of 116, a size of 4. And at this point, the sequence number that the transmitter wants to send next is 120. The last acknowledgement that we've received is still 108. The next byte that we're expecting, or the byte below which that we've received everything in order is 114, but the most recent byte that we've received out of order is now 120. So recall, NRX and NS are the same as long as we've received all of our frames in order, but as soon as we receive an out of order frame, NS is updated, but NRX stays the same. So NRX only ever progresses once we've received things in perfect order, but NS is allowed to jump ahead if we receive things out of order. And then when we see a difference between the two, we know that we've got a gap, basically. And so one thing to point out at this point is if we look at the last byte that we've received an acknowledgement for, which is 108, and the next byte we'd like to send, which is 120, we've now hit our 12-byte window size. And so this is the point when the difference between these two numbers equals our window size. This is where the transmitter has to stop. So the transmitter is not going to send any more segments until it receives an acknowledgement from node 2. Now I've run out of space here, so what I'm going to do is I'm going to go to the next slide, and I've just copied over the last transmitted packet and the values for NTX, NA, NRX, and NS. So that's what we've got here. So we're picking up where we left off. So the transmitter now is not going to proceed until it receives an acknowledgement. The node 2 sends an acknowledgement, but remember, node 2 will only ever acknowledge the or will base its acknowledgements on the value of NRX. So it wants to tell the transmitter the next in order byte that it expects. And so when it sends its acknowledgement, its ARQ value is going to be equal to 114, not 120. And so this is basically the receiver's way of saying, you know, I've received all of the bytes up to byte number 113 in order. All that's taken care of. I now need byte 114 because I haven't received it yet. I know I've received other bytes higher than 114, but I want to fill in the hole. And so the transmitter at this point, and I'll just capture the value for our variables. So the transmitter wants to send 120. It's now received an acknowledgement for 114, and the receiver values haven't changed, 114 and 120. And so the transmitter now will, or the transmitter buffers all unacknowledged segments. So every segment that it has not yet received an acknowledgement for, it sort of keeps in a buffer just in case it has to be retransmitted. And so up until this point, the transmitter has sent a segment with sequence number 108, a second segment with a number 114, and a third segment with a sequence number 116. And so when it receives an acknowledgement with a value of 114, it knows that that first segment has been received, the segment with sequence number 108, but it knows that the second segment with sequence number 114 hasn't been received because the receiver basically said, I want 114 segment with sequence number 114 now, and the transmitter's like, oh, I thought I sent that. I guess you haven't received it. And so that is what the transmitter is going to resend. And so it's going to look in its buffer, pull out the segment with sequence number 114, and resend it. And so this is a retransmission with sequence number 114 and a size of 2. This time it arrives successfully. So at the transmitter, we still want to send 120. We've still only received an acknowledgement for 114. At the receiver, we've received up to byte 119, so NS is 120. And now we've successfully received our missing segment. So rather than NRX just increasing to the end of this received segment, it's going to increase all the way up to the maximum in order byte that it's received. So it received, now that it's received this segment with sequence number 114, it's already received the sequence number, or the segment with sequence number 116. And so the NRX value goes all the way back up to 120, because basically what we've done is we've filled in the gap. And so NRX now has been able to zip all the way up and join 120. That means that when the receiver sends its acknowledgement, it's now not going to acknowledge 116, it's going to acknowledge all the way up to the maximum in order byte value that it's received. And so its acknowledgement is going to be equal to 120. And so we essentially acknowledge not only the retransmission of that middle segment, but the successful reception of the segment with sequence number 116. And so just to conclude the example, at this point, everything is all caught up. The transmitter is ready to send byte 120. We've acknowledged that the next byte we're expecting is 120. The next in-order byte we're expecting is 120. And the maximum byte that we've received is 119, so NS is equal to 120 as well. And so that dove down into the details a little bit. I wanted to sort of go through the sequence numbers just so you can see how they can progress, but I hope I didn't obscure kind of like the big picture thing of what was happening. So essentially we sent, in that middle portion, we sent 3 segments and we missed the middle one, right? So we sent the first segment, the second segment was lost, the third segment was received successfully. When we sent an acknowledgement, it informed the transmitter that it was the middle segment that was not received correctly. That middle segment was retransmitted, and then the next acknowledgement to follow acknowledged not only the fact that we got the middle segment, but that we received the third segment successfully as well. So our acknowledgement slid all the way up to the top of the in-order bytes that we received. So if that was a lot of detail, please rewind the video, go through it slowly. Definitely make these diagrams, step by step, draw your own arrows, update your own sequence numbers, make sure that it all makes sense. This is, if it helps, go back to Module 9 and look at the example there. This is selective repeat ARQ, which is the same as the example we worked through in Module 9. The only difference is this business with the byte-based sequence numbers.